Okay, JPEG. So one of the compression image is JPEG, which is very popular. Okay, so JPEG stand for Joint Photographic Expert Group. So why do I choose JPEG? Because JPEG is not the best one, but it is a popular, and most of the application use JPEG. So JPEG is not only use one technique, so it is a combination. Okay, what we have learned before, okay, where you will have the encoder and decoder. So in encoder, you will do the image or block preparation, means you will identify what is the input image type, okay, and then you will do the block preparation, means you will divide the image into blocks. Okay, then you will do the forward DCT, where you will apply the transformation technique, okay, on the DC using the DCT transform. So output of this, it will do the quantization. Okay, so output of quantization, you will do the entropy coding. So entropy coding, you will divide into two. So one is the vectoring and the other one is the Huffman coding. So once you complete the entropy coding, you will prepare it in a frame grabber. So after you encode, you will do the decoder. So you will do the inverse process, okay, of the encoder, where from the frame grabber, so you will do the Huffman, okay, and then with Huffman, you will do the differential decoding and run length encoding, okay, the same as the vectoring that you did in the encoder. Then you dequantization, okay, dequantization, and do the inverse DCT. Okay, lastly, you will get the output. So JPEG is unlike 1D audio signal. So it is a digital image which consists of Fij, which is not defined over the time domain. So it defined over a spatial domain. So in example, an image is a function of 2D, okay, I and J, or it can be in XY. So for instance, the 2D DCT is used as one step in JPEG to yield frequency response, okay, that is a function of FUV in the spatial frequency domain indexed by two integers UV. Okay, so this has been taught in your image processing, okay, where you will transform the spatial domain into a frequency domain. So in other words, when you transform your image in spatial to a frequency, so it will reduce the size as well. So that's why you need to have a transformation, okay, in JPEG. Okay, so spatial frequency indicates how many times pixel value change across an image block. So in DCT, this notion means how much the image content change in relation to the number cycle of a consigned wave per block. So the effectiveness of DCT, why do you use DCT in JPEG? So there are three observations. Okay, why you use DCT transform instead of WHT or any other transformation coding? Because it is useful image content which change relatively slowly across the image. So although DCT is much more complex compared to WHT, but the content change with relatively slowly. So it will be produce a smooth image. So, and also psychophysical experiments suggest that humans are much less likely to notice the loss of very spatial frequency component. So that's why, okay, we use the DCT. So JPEG approach to the use of DCT is basically to reduce the high frequency content and then efficiently code the result. Okay, then spatial redundancy means how much of the information in an image is repeated. If a pixel is read, then its neighbor likely read also. So as frequency gets higher, it becomes less important to represent the DCT. Okay, if your image frequency is high, okay, it is less important. So it means that you can remove or truncate, okay, the less important information. So that's why DCT is coefficient is accurately used. And the third observation, by visual accuracy in distinguish closely spatial line is much greater for gray than color. So this is the diagram, okay, of the one that we discussed before. Okay, where you have the source, you will do the image or block preparation. In block and image or block preparation, you will have two process. One is the image preparation, and then you will do the block preparation. Okay, but you can directly go to the block preparation without image preparation. So output of this, you will do the forward DCT. Okay, then your image will be in a frequency domain. So once it is in the frequency domain, you will do the quantization. Quantization means you will reduce the range, the large range of data into a smaller range. So what you will do, you will quantize depending on the table that you create. Okay, you design. So once you finish quantization, so you will do the vectoring. Vectoring means you will transform the 2D into 1D. So with this vectoring, you will separate it into two. One is the differential encoding and the second one is RLE. Okay. So then you will do the Huffman coding for both. Okay, and the Huffman will depends on the table that you created before. So once you finish on the entropy coding, so this is an entropy coding, then you will prepare in a frame builder. So then you will get the encoded bit stream to be sent or saved on your computer. So let's look on the first step, which is the image or block preparation. So you will have the source image. So your source image can be any type of image. So it can be in a monochrome, or it can be an index or CLUT image, or it can be in a RGB or YUV. So you have to identify first what type of image your input, your source is. Okay, so this is in image preparation. Once you complete, then you will do the block preparation. Block preparation means you will divide, okay, your image into blocks. Okay, so it will be in a 2D matrix which divide into n, okay, which is each of the block which you have 8 times 8 blocks. Okay, so from this you will do the TX order. So you will sort it into block 1, 2, 3, 4 until block n. Okay, so once you complete, each of the block will be transformed, okay, using forward DCT. Okay, so let's consider that you already done the image preparation. So then you will do the blocking, where you will divide, okay, into 8 times 8. So since image has many low frequency component and relatively low frequency component, DCT is used to convert the original into frequency domain using DCT equation. And high frequency component are quantized with a small number of bits, thereby achieving effective compression without degrading. So you will divide your image into blocks. So once you divide, then each block will be transformed in using the DCT. Okay, so then you will sort the image. So you will have the DC and AC, and the rest will be the DC. So once you transform into DCT, then your image will be in DC and AC coefficient. So DC coefficient means of all 64 values averaging color, luminance, chrominance associated with an 8 times 8. So if you remember, once you transform into a frequency domain, your image is no longer as a spatial. So once you get the D transform, it will be image with full of information, information of the color, luminance, and the chrominance. So it will be sort into DC and AC. Okay, so this I will the arrangement is increase FH horizontally spatial frequency. So as you go down, the frequency will become lower. Okay, so this we consider as high frequency, which have more information. So consider a typical image from comprising 640 times 480. Assuming a block of 8 times 8 pixels, the image will comprise around 4,800 blocks. Okay, each for a screen width of say 16 inches. So we'll occupy a square of 0.2 times 0.2 inches. Okay. So you will transform into a DCT. So it will be like this. Once you transform into DCT, so this will be the DCT coefficient. Okay. So to reduce number of bit per pixel. So next you will do the quantization. So once you get the DCT coefficient, next step is to do the quantization. So the human eyes respond primarily to the DC coefficient, okay, and the lower spatial coefficient. Hence, a higher spatial frequency coefficient, which is below a certain threshold, that the eyes will not detect it, and it will be dropped. Okay, so instead of comparing each coefficient with the coefficient threshold, a division operation with quantization table is used to reduce the size of DC and AC coefficient. Okay, so quantization means you will reduce the range, the large range to a smaller range. Okay, so let's say you have this DCT. Okay, as you can see, this is AC and the rest will be the DC. So DC is a less information compared to AC. So the two default tables, on for luminance coefficient and the other for two chrominance coefficient. So with this DCT you can reduce, okay, you can remove the duplication, okay, the zero value. Okay, how? Is by, before you reduce, you have to quantize. So quantize means you will use a table and divide it by the DC.